Magnetostatic loudspeaker simulation in QuickField. Magnetostatic loudspeaker consists of a set of permanent magnets and a planar diaphragm. Conducting strips carrying current are attached to the diaphragm. The current in the diaphragm interacts with the magnetic force created by the permanent magnet, causing the diaphragm to vibrate. Our task is to calculate the magnitude of the force as a function of the electric current value. Well, in real device, AC current flows in the conducting strips. But the magnitude of the force depends on the electric current magnitude. It doesn't depend on the frequency. So we can simulate DC magnetic problem instead of the AC problem. And to simulate DC problem, I need only to know the permanent magnet coercive force and the remnant flux density, and I need to know the electric current value. The model features symmetry, so I will include in the model only one strip and two halves of permanent magnets. Okay, let's start QuickField now. In QuickField, I create new problem. Problem name loudspeaker. Next. Problem type is magnetostatics. Length units are millimeters. Model class is plane parallel. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD DXF file. Click in the geometry model window to make it active, then follow to the file, import DXF. Here is the file, open. And here is the geometry model imported. You can recognize permanent magnets, diaphragm, and conducting strips. Okay. As I said, we need only one strip in the model. So I'll switch to insert mode. And draw vertical axis of the symmetry. Here and here. I need only the part located between these axes. Switch to select mode, select the remaining parts and delete them. Okay. Also, I need to add the air block. Again, switch back to the insert mode and draw the air block boundaries. Here and there. Now let's assign labels. For labels, we will explain the geometric object's meaning and provide material properties. Switch to select objects mode. Click the object to select and assign label. This is air. And this block is air too. Now this is the permanent magnet, which magnetic north pole is directed up. Permanent magnet up. And this is the permanent magnet which north pole is directed down. Permanent magnet down. And we have the conducting strip. Next, I should assign labels to the axis of the symmetry. Select. Hold the Ctrl button to select multiple objects at the same time. Select. These edges are symmetry. And I will assign label to the top and bottom boundaries. External boundaries. Okay. Now let's provide physical properties for these labels. Double-click the label name in the tree. Relative magnetic permeability of the air is 1. Okay. Relative magnetic permeability of the strip is 1. It is made of copper. And the total current in the strip is 0.1 ampere. Total current. Okay. Magnet permeability is 1.05. Coercive force magnitude is 500 Q-amperes per meter. Directed up 90 degrees. Okay. Magnet down. Same magnetic permeability. Same magnitude of the coercive force, but the direction is minus 90 degrees. Okay. At the axis of the symmetry, magnetic flux goes parallel to the axis and has zero normal component. That is equivalent to the zero vector magnetic potential. Okay. Far away from permanent magnets, magnetic field fades to zero. So again, at the external boundaries, I will specify zero magnetic potential. Okay. Geometry model and the data are ready. Before I start the analysis, I should build the finite element mesh. Just press this button and the mesh is constructed. Now save all problem files and solve the problem. Let's take a look at the results. And here you can see the magnetic field lines. You can adjust the field picture and switch on, for example, the color map of the flux density. You can see the correspondence between the colors and the values here in the legend. My task is to calculate the force acting on the strip. Let's zoom in. Here is the strip. I will use the contour tool. Click inside to select the strip. Follow to the integrals. And here is the mechanical force acting on the strip. The force is pointing down. If you change the current polarity, the force will be pointing up. If you search for the magnetostatic speaker on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the results, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.